I think this one's easy to memorize because if you remember in Calculus 2, we were calculating curve lengths in the xy plane, and we said that the curve length was just the integral of the square root of 1 plus dy dx squared dx. So now we're not doing curve length anymore, we're doing surface area, but I think this is easy to remember if you notice the similarities in what we're doing here. Notice the similarities. Now we're talking about a surface, so we've got z as a function of x and y, and we're just taking the derivative, or the partial derivatives, and then squaring them, and then you add a 1, and then you take the square root of the whole thing, and that's your integrand. So helpful memorization tricks. Okay, I guess everybody's got this copied down, so we can try to use it. Find the surface area of the given surface above the region R. So I'm going to take my formula, double integral over R of the square root of 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared dA. So, what is the partial of z with respect to x? -1. And so what would that be squared? Squared, that is just 1, right? And then the same thing goes for y. We have the same partial derivative with respect to y squared. So my integrand is going to be pretty simple in this case. So we'll again take the double integral over this region. This time my integrand becomes 1 plus 1 plus 1.
That works. Yeah, that can.
So you could either do dx dy, or you could do dy dx. And I think either way is just about the same. So I'll just arbitrarily write down, we can just write it out both ways. Just to practice, we'll just write it out both ways for the heck of practicing this. So this is going to be the square root of 3, right? And that's just a constant. So you could actually just, pull that out of the integral if you wanted to. I could just write square root 3, my constant, times the double integral of 1 dx dy. So that makes the antiderivatives really easy. But then my outside integral is in terms of y. And so I'm going to say that my y as a constant can be anywhere from -1 up to +1. So those will be my bounds of my outside integral. And then if I try to write x, well, the lower bound on x is 0, and the upper bound on x is going to be the square root of 1 minus y squared. So the square root of 1 minus y squared is going to give me the right side semicircle of a unit circle at the origin. So remember, this circular part, the circular part is given by x squared plus y squared equals 1 squared, because my radius is 1. And then, again, to rearrange this and solve for x, I would have the square root of 1 minus y squared. So that's how I came up with that upper bound of that inside integral. Okay? Like I said, we're going to practice, though, and we're going to write this two different ways. So this is the same thing as writing the square root of 3 times, let's do dy dx this time. So my first integral is going to say, in terms of constant numbers, what's the lowest x can be and the greatest number x can be, and that's going to be between 0 and 1. And then I have to determine what is y. And so for my lower bound, I'm going to need the bottom semicircle, and for my upper bound, I'll need the top semicircle. And so now I just rearrange that equation for the circle and solve for y. The lower bound is going to be negative 1 minus x squared, and the upper bound is going to be positive 1 minus x squared, to give me the lower semicircle and the upper semicircle. But one thing I'll point out, though, as the thought occurs to me, is that if I take the double integral over some region in the plane of 1 with my integrand, that whole thing, this bit right here, that's just equal to the area of the region. All right, that's just one way of finding the area of that semicircle. And so the area of a circle is pi r squared. In this case, my radius is 1, so the area of that circle would just be pi, but I'm also just taking half of the circle, so the area should be pi halves. And so without having to do any extra work, I know that this is going to be square root of 3 over 2 times pi. Just by using my knowledge of the formula for the area of the circle, and knowing that if I take the double integral of 1 over some region in the plane, it just gives me the area of that region in the plane.
It's like, it looks like the second fundamental theorem of calculus, but applied to a multivariable function. Say like,
yeah, and we'll talk a little bit more about what I would call them like extensions of the fundamental theorem of calculus to higher dimensions. There's going to be a lot of those in chapter 15, and so we'll talk more about that too. But that's a good point. Yeah, Stephen?
Did you write this in polar coordinates?
In polar. So okay, the region has some radial symmetry. You could say that the radius r could go from lower bound 0 to upper bound 1, and theta, my angle, could go from negative pi halves to positive pi halves, and that would sweep out the region. The only issue is that this surface, that function of x and y, that doesn't really have good radial symmetry. And so you could write it in polar coordinates, but you're going to end up with like r cosine theta and r sine theta. And I don't think that the integral would turn out very nicely. But you could try it. You could try it. You know, I'm not going to do it in class, but we'll do another example with polar coordinates here in a second. Good questions. Okay, but that means that the square root of 3 over 2 pi, that would be the surface area of this plane, you know, z equals 2 minus x minus y. That would be a plane in three-dimensional space. And so the surface area of the plane is just going to be some slanted area over a semicircle. Okay. New example. It says find the surface area of the given surface above this region. And this time we're only going to set up the integral. We're not actually going to try to solve this. Because I think sometimes with these problems the integration gets nuts. So next week I'll probably have some of these types of problems on your test where I ask you to only set up the integral. And so you'll just do exactly what we're about to do here. So I need my formula. I need the double integral over some region of the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared dA. That's going to give me my surface area. What is my partial of z with respect to x? Negative 2x. And so if I want to square that, then this would be 4x squared. And then my partial with respect to y would be 1. And so if I square that, 1 squared is also 1. So if I want to rewrite this, I'll write the square root of 1 plus 4x squared plus 1. And I have to choose some order of integration. If I happen to choose, let me think about this. Always takes me a moment. If I happen to choose dx dy, that means for my y variable, I could just easily throw down the constants -1, +1. But then for my x variable, the lower bound would be 0, and the upper bound of my x variable would be a piecewise function. And since the upper bound of my x variable would be a piecewise function, I would actually have to write 2 double integrals. That's kind of like the problem I showed you at the beginning of class today. So if I wanted to do this dx dy, I would actually have to add up another double integral. I'll call it 2 plus 4x squared dx dy. And this time I'm going to intentionally remember that for the first part, y is allowed to go from -1 to 0. X is allowed to go from 0 to, and then I have to figure out what is the equation for the line that makes the upper bound of x for this part of the region. And that line has slope +1 and it has y-intercept -1. So that line is y equals x minus 1. But I need to solve for x. And so I can say x is equal to y plus 1. And so for my upper bound here, I'll make that upper bound y plus 1. OK, what about this part, the upper part of this region R in red? So again, y now, for that red part of the region, y can be anywhere from 0 to +1. And x can be anywhere from 0 to, let's figure out the formula for this line. And the formula for that line is y equals -x plus 1. And in terms of x, that's x equals -y plus 1? No, right? Yeah. Yeah, okay. Yeah, x equals -y plus 1. So that means the upper bound here can be like 1 minus y. But I had to write 2 double integrals because I had to break up my region into 2 sections. And I had to do my region in 2 sections because my upper bound of my x variable was going to be piecewise. Okay, so that's how I would do it if I was going to do it dx dy. I should also get the same answer if I tried to do this dy dx. And so let's, for the sake of practice, let's do it dy dx now. Okay. Same integral. Now dy dx. And my x values can now be anywhere between 0 and 1. Since it's the outside integral, I put constants as the upper bound, lower bound. And then I have to say that y can only be between this lower bound line, and that lower bound line is the line y equals x minus 1, and my upper bound line, which is the line y equals negative x plus 1, so 1 minus x. And so solving this one double integral should give you the same result as if you solve those two double integrals we used with swapping the order of integration. Does that make sense? Any questions? So either way you set that up, that would be full credit on the exam. All I'm asking with this question is to set up the integral, and that's set up enough for me. If you actually wanted to solve that integral, it might get kind of messy. And so if it turns out like that, if it turns out that the antiderivatives are really messy, then I won't actually make you solve it. In real life, in practice, you would solve it with some sort of numerical method like a Riemann sum or Simpson's rule, etc. Okay. Find the surface area of this given surface, but we're only going to think about the portion of the surface that is above the xy plane. And above the xy plane, that means z is greater than 0. Yeah.
Above, yeah.
Yeah. It would intersect the xy plane, yeah. It intersects the plane. At z equals 0. And if I want to solve this, I actually need to find out what that intersection is, because I need to know what is the region that I'm doing a double integral over, right? So my surface area is going to be some double integral over some region R of square root 1 plus partial z partial x squared plus partial z partial y squared dA. Okay, so we ask what is that region? We have to find the region that lies inside the set where this surface happens to intersect the plane. And so what I would do is I would set z equal to 0 and write 0 equals 1 minus x squared minus y squared. But if I rearrange that a little bit, I can get x squared plus y squared is equal to 1 squared. And that's the formula for a circle centered at the origin with radius 1. So that is my region that we're going to integrate with. And my surface is z equals 1 minus x squared minus y squared. That's a paraboloid. And you might notice that in this case my region has radial symmetry about the origin, and also my surface has radial symmetry about the z-axis. And so this is a really good opportunity to use polar coordinates. So I can rephrase this surface equation as 1 minus r squared, since r squared is just x squared plus y squared. And then for my region, I can describe my region by saying r is less than 1, and theta is between 0 and 2 pi. So if I want to write a double integral over this region, I'm going to use the order of integration r dr d theta. Don't forget the extra r that you get whenever you integrate with polar coordinates. And then in terms of my radius, it goes from 0 to 1. In terms of my theta, it goes from 0 to 2 pi. And my integrand is going to be 1 minus, Sorry, I have to think about what this means for my surface area, because I'm not trying to find the volume anymore. Volume would be easy. It would be 1 minus r squared for my integrand. This time my integrand is a little bit crazier. This has to be the square root of partial z with respect to x squared, and partial z with respect to x was what? Here's my negative 2x. Okay, negative 2x. And so then if I want to square this, then that would be positive 4x squared, right? Okay. So 4x squared. And you know that this formula right here for my surface, it's symmetric with respect to x and y. And so the partial derivative of z with respect to y squared would just be what? 4y squared. Cool. So then I'm taking in my integrand the square root of 1 plus partial z with respect to x, 4x squared, plus partial z with respect to y, so 4y squared. So I've got plus 4x squared plus 4y squared. That's the same as plus 4r squared. Remember, r squared is x squared plus y squared. And so I'm going to write 1 plus 4r squared. So polar coordinates are really going to help us here. It's going to make the problem very much easier to integrate. What strategy should I use to take the inside integral, inside antiderivative?
Tangent.
Not a trig sub. It's easier than that. It's what? A u sub, yeah. Yeah, don't forget, I get this little r. You get that r from integrating with polar coordinates, and that's really helpful sometimes. So my u and my u sub, I think, should be 1 plus 4r squared. So that means du is going to be equal to 8r dr. I could say 1/8 du is equal to r dr. So if I try to rewrite this, it's going to be 0 to 2 pi, antiderivative, then the square root of u times du d theta, and I pick up the 1/8 constant. My lower bound of integration is going to be 1 plus 4 times 0 squared, so it's going to be 1. My upper bound of integration is going to be 1 plus 4 times 1 squared, so it'll be 5. Don't forget to change your bounds. And the antiderivative of u to the half is going to be u to the 3/2. And then I have to also pick up a constant. It's going to be a 2/3 constant. When I take the antiderivative, again, this is going to be at 5 and at 1 d theta. This is going to be a little bit messy because 5 doesn't have a nice square root. I can simplify that, can't I? So that's going to be 1 over 12 times, integral from 0 to 2 pi of the square root of 5 cubed, or I could say 5 square root 5 minus 1. And so, you know, the antiderivative would just be multiplying by a theta, and then whenever I replace theta with 2 pi and I replace theta with 0, it's essentially just multiplying that integrand by 2 pi. And so my final answer is going to be pi over 6 times 5 square root 5 minus 1. So what we had was z equals 1 minus x squared minus y squared. And so we were just calculating the surface area of this little part of the paraboloid that sticks up above the xy plane. And that's what the surface area is. It is pi over 6 times 5 square root 5 minus 1. Kind of bizarre. Any questions? Okay. So, another example. So we're going to consider a sphere centered at the origin with radius 5. So there's my sphere. This time that's the z-axis, let's say, and then this would be the x-axis. We're also going to consider a cylinder centered at the z-axis with radius 3. And so, if I have a cylinder centered at the z-axis, then slicing it is going to give me something like this. And it says, find the surface area of the portion of the sphere that's trapped inside the cylinder above the xy plane. And so this horizontal plane I wrote could be, or that horizontal axis could be like x or y axis, right? What I'm doing is I'm taking the trace of these three-dimensional objects along the xz plane or the xy plane, and it's radially symmetric, so it doesn't really matter. Maybe you can visualize it really quick. So, what if I type, let's get rid of that, x squared plus y squared plus z squared is equal to 25. That gives me the sphere with radius 5 centered at the origin. And then if I want a cylinder with radius 3, I would write x squared plus y squared is equal to 9, right? And so, change the color a little bit. Ta-da. Okay. So what I'm asking in this problem is above the xy plane, inside the cylinder, what is the surface area of this little portion of the sphere, right? What's the surface area of that portion of the red sphere that is inside the blue cylinder? Okay, so that's what I was trying to draw, like a cross-section slice of. What I want the surface area of is just this little portion. Okay? All right. So, we're going to set up this problem same way we did before. This time I'm going to draw an xy plane so that I can show you the region that we are integrating on is going to be the circle with radius 3 centered at the origin here. And then the surface that we want to find the surface area of is going to be the square root of 25 minus x squared minus y squared. Right? That would give me the top half of the sphere, and I only care about the part that's above the xy plane anyways, and so that's going to work. Okay, so here we go. The surface area is given by a double integral over the region of square root of 1 plus partial with respect to x squared plus partial with respect to y squared dA. So we might ask, what is the partial with respect to x? Yeah, it's not super easy because we have to use chain rule. And so I'm thinking, yeah, to take the derivative of my outside function first, I have to take the derivative of the square root, which is going to be 1 over 2 square root 25 minus x squared minus y squared. And then times the derivative of the inside, which would be negative 2x. And then the 2's cancel. And then we get negative x over the square root of 25 minus x squared minus y squared. Of course, for my formula, I actually need the partial with respect to x squared. So let's go ahead and take it squared. Squaring it will get rid of the minus sign. It'll get rid of that square root, and it'll make that x squared. Okay. Without having to duplicate all the effort, I just noticed that this is symmetric with respect to y. And so I can write the same thing. The partial of z with respect to y squared should be y squared over 25 minus x squared minus y squared. Okay. Now, in my formula, I have to add those together. Adding them together is going to be really easy because they have the same denominator, so I don't have to find a common denominator. I just have to add the numerators, which is x squared plus y squared. And I'm getting the feeling that this would be nice to change into polar coordinates because the sphere is radially symmetric about the z-axis and the cylinder, or my region R, is radially symmetric about the z-axis. And so let's change this to polar coordinates. And when I change to polar, I can write this double integral. Order of integration r d theta. My integrand, I'm going to write as the square root of 1 plus r squared over 25 minus r squared. R is allowed to be anywhere between 0 and 3. Theta is allowed to be anywhere between 0 and 2 pi.
2r squared? X squared.
Yeah. I skipped a step, but yeah, in my formula I'm adding those partials squared, and so I'm adding x squared over 25 minus x squared minus y squared, and y squared over 25 minus x squared minus y squared. And so I just have to add the numerators. X squared plus y squared gives me r squared, and then the denominator is going to be 25 minus r squared. So that's how I ended up with that. So what I want to do here is I want to manipulate the inside of the square root a little bit. So where I have 1 plus r squared over 25 minus r squared in my radicand, let's multiply that 1 by 25 minus r squared over 25 minus r squared. Notice that's still the number 1. But now I can add these together, since they have a common denominator, and I would get 25 over 25 minus r squared. And this is in my radicand, right? So I could just, put a little square root over it, and now this is my whole integrand. And I could, well, do I want to do that? Let me think. Yeah, I guess so. Okay. This is equal to the same thing as 5 square root of 1 over 1 minus r divided by 5, all squared. I can't tell if that's helpful or not. We'll see. But I think we're going to use a u sub.
And then
Yeah. We're going to use a u sub because I have this little r hanging out here, and so that's perfect. I think that that's going to turn out nicely whenever I take the derivative of my u sub. But what should be the u in this substitution? I'm going to just try this, and if it doesn't work, we can try something else. But I'm going to try making this my u. So we'll say u is equal to 1 over... Actually, you know what? Scratch that. Let's just do the denominator. And heck, sorry, I keep changing my plan a whole lot. But if I have 1 over stuff inside the radical, I can rewrite that as 5 divided by radical 1 minus r over 5 squared. Let me just go ahead and rewrite this whole thing so that we're not getting confused here. So the way I'm rewriting this double integral is going to be 0 to 2 pi, 0 to 3. Pull the 5 outside because that's a constant. Inside my integrand, I'm going to have this raised to the negative 1/2 power 1 minus r divided by 5 squared r dr d theta. Okay. Now, what I'm going to make my u for my u substitution is going to be 1 minus r over 5 squared. So that means du is going to be sorry, I keep modifying things. I don't know if I like how it looks, but that's going to be negative 2 over 25r. Am I right? dr. Which means I can replace r dr, I can replace that with negative 25 over 2 du. So what I pick up over here is negative 5 times 25 is negative 125 over 2. Integral of 0 to 2 pi of integral 0 to 3 of this time u to the negative 1/2 power, and then I replaced r dr with negative 25 over 2 du d theta. All right. That's a good place to stop because now we just have to use antiderivative power rule to get rid of that middle integral.
the bonds too.
Oh, yeah, thank you. Very important. What are my new bounds? Lower bound 1, which is 16 over 25. Nice.